Hello and welcome back to the Biochemistry for Health Sciences channel. In order to understand enzymes, we shall look at a few examples. In this video, we shall discuss the enzyme chymotrypsin. Before we talk about chymotrypsin, let's review a little bit of basic chemistry. There are hundreds of chemical reactions that happen in the human body. So basically, a chemical reaction you can see is shown by an arrow. Everything on the left-hand side of the arrow, these chemicals are called the reactants. And everything on the right-hand side of the arrow, those chemicals are called products. Enzymes make the chemical reaction go much faster. So if the reaction is catalyzed by an enzyme, then instead of the word reactants, we sometimes use the word substrates. So basically, reactants and substrates is the same thing. The enzyme chymotrypsin catalyzes a reaction where the peptide bond, this one here between this carbon and nitrogen in a protein substrate, is broken by water. So this is called a hydrolysis reaction, since water is used, hydrolysis reaction. And when this bond is broken by water, we get the amine and the carboxyl group. Because as you know, this is the amide. The amide is broken down into amine and carboxyl. So this is basically the reaction that chymotrypsin catalyzes. Later on, when we look at metabolism, we'll come across many biochemical reactions. Sometimes besides the reaction with the name of the enzyme, we see this value here, this delta G reaction. So for example, for chymotrypsin, this delta G reaction for a typical protein substrate is minus 12 kilojoules per mole. In our body, we will come across some reactions where the delta G reaction is a high negative number. So here's one example, very high negative, minus 22, minus 34. Here's another very high negative, minus 17. Sometimes we'll see these numbers are positive. This is a small positive number, plus 3. Here's another small positive number, plus 1, and so on. Here's a minus 3. So some of these numbers are very small. They are basically close to 0. Some of these delta G's are maybe positive, negative, or close to 0. So what does this delta G reaction indicate? The delta G reaction is the energy of the product minus the energy of the reactants. So in this case, the product is B, so energy of B minus the energy of A. Since B has higher energy than A, this delta G will come out to be a positive number. So those reactions where the delta G is positive, these are called non-spontaneous reactions or endergonic reactions. And in this case, in order to convert A into B, we require to put in some energy into the reaction. Without putting in external energy, A will not become B. If the energy of the product is more or less equal to the energy of the reactants, then the delta G reaction will be a very small negative or positive number, very close to zero. In that case, the reaction can either go A to B or B to A. The reaction can go either direction. We can call such reactions equilibrium reactions. The chymotrypsin reaction, which is the breaking of a peptide bond, that delta G is a relatively high negative number, minus 12 kilojoules per mole in case of the chymotrypsin reaction. Reactions where the delta G is negative, these are called spontaneous reactions or exergonic reactions. In this case, there is no external energy needed to convert the substrate into the products. No external energy is needed to break the peptide bond. So the substrate will get converted into products. What are you doing, Quirly? Aha, I see. So you are waiting for the peptide bond to break. So it looks like you added your substrate in water. What temperature do you have this at? 37. That's the temperature of the body. So you're waiting for the peptide bond to break, and that's not happening. Interesting. What is the reason for that? Well, negative delta G reaction simply means the reaction is spontaneous. It will happen. But delta G reaction does not say how long will it take for the reaction to happen. Under physiological conditions, that is aqueous solution, because our body is filled with water, pH around 7 and body temperature 37 Celsius, this reaction here, breaking this peptide bond with water, that will take a few years to happen. Yes, Curly, it will take a few years to happen. So waiting for 1 hour, you're not going to see anything. What is the reason? Why does it take so long? So let's talk about why it takes so long for this reaction, this spontaneous reaction to happen. According to basic chemistry, reactions happen because of what we call the collision theory. That means reacting molecules are always moving around. So this protein is moving around, water is moving around, they're always moving around, and sometimes they can collide with one another. And when they collide with one another, and if the reacting molecules have sufficient energy, and if they collide the right way, what we call the proper orientation, only then will they react. And when they react, they may give you the products. So, for example, in this reaction here, if the oxygen of the water, which is slightly negatively charged, comes and hits the oxygen of the peptide bond, the amide linkage, there is no reaction going to happen because these two are not going to meet. This is negatively charged and this is also negatively charged. So that's going to be quite impossible for them to come towards one another and collide. Similarly, if the water came and tried to come and in this direction, we have this group that is blocking the water from attacking this carbonyl carbon here, this carbon here. Same problem here. We have this R group that is blocking the water from attacking the carbon. So because this carbon is sp2 hybridized, this shape here is what we call trigonal planar. It looks like a triangle, a planar triangle. So one good possibility of a reaction to happen is if the water molecule comes from the bottom or the top and hits this carbon. So besides the proper orientation, proper collisions to happen, there is also a good possibility that most of these reacting molecules, the water and the proteins, under physiological conditions of 37 Celsius, there may not be enough movement and may not be enough energy for them to collide. In addition, even if water were able to hit this carbon here, water is not a reactive substance. In chemistry, we say water is a weak nucleophile. So compared to physiological conditions where reactions will take a long time to happen, very difficult for reactions to happen, organic chemists use conditions that are very different than physiological conditions. For example, instead of water, they use organic solvents such as hexane, dichloromethane, ethyl acetate, and so on. Instead of pH 7, very often they use strong acids and bases. And instead of 37 Celsius, the temperature used for organic chemistry reactions can range anywhere from minus 90 to as high as 200 degrees Celsius. Very different conditions than what we see in the human body. So let's talk a little bit about reaction rate, what we also call the velocity of the reaction. Okay, so the rate of the reaction or the velocity of the reaction is how fast this reaction occurs. How fast is this peptide bond broken to give you the products, the amine and the carboxyl product. So the reaction rate or the velocity of the reaction is given by this equation here, which is K. K is the rate constant, multiplied by the concentration of reactants raised to the power of X. X is the order of the reaction, and this concentration of reactants is represented by these square brackets. So this is the concentration of the starting material. So basically the reaction velocity is equal to the rate constant multiplied by the concentration of the starting materials, the substrates or the reactants. So in case of chymotrypsin, the concentration of the reactants will be the concentration of this protein substrate and water. Now water, however, is the solvent, and that does not affect the reaction rate. So we can ignore water. So the velocity of this chymotrypsin reaction would be dependent on the K multiplied by the concentration of the protein substrate. Now, although K is called a rate constant, it's not really a constant number. K is actually given by this formula, A times e to the power of minus EA over RT. So if we put this K value here, we get our velocity of the chemical reaction, which is substrate concentration times A times e to the power of minus EA over RT. So in this equation here for the velocity of the reaction, A is called the frequency factor. This is a constant number. It gives us an idea of the collision frequency and orientation. So as long as the temperature doesn't change too much, like what we see in the human body, this A is a constant number. E is a mathematical constant called the Euler's number. It's about 2.7. R is also a constant. That's a gas constant. It's about 8.3 joules per Kelvin per mole. So all these here, A, E, and R, these are all constant numbers. So basically, if all these are constant, then the velocity really depends only on the variables, and that's the substrate concentration, EA, and the temperature. And we'll see that in this formula, the reaction rate or the velocity will increase if S increases or T increases. If the substrate concentration or temperature is higher, then the velocity increases. But if the EA is lower, then the velocity increases. So let's look at this variable called EA. So EA is called the activation energy. To explain how fast reactions happen, the velocity or the rate of reaction, we bring in this concept that we call activation energy. So before the reactant, the peptide bond is broken into the amine and carboxyl, we say that there must be some sort of a transition state form where the peptide bond is almost broken, not really, and the hydrogen of water is connected to the nitrogen, and the hydroxyl of water is connected to the carboxyl. So this is called the transition state of this reaction. So we hypothesize that there must be some sort of a transition state that is formed. This transition state we cannot observe or we cannot isolate. We simply hypothesize there must be something like this form before the products are formed. As you can see, the transition state has a much higher energy compared to the substrates or the products. So for this reaction to occur, the reacting molecules, these molecules here, they will have to get enough energy to climb up the top of this hill where the transition state is. And once they reach the top of this hill, the energy of the transition state, then they can easily come down to give you the products. So that's why the higher the substrate concentration, the more likely we can have molecules of the substrate that has reached the top of the hill. Similarly, the higher the temperature, the more the movement of these molecules, that means the more likely that these molecules will reach the top of the hill. And similarly, if the hill is very high, then it's harder for these reactant molecules to reach the top of the hill. But the hill is very low. If the EA is very low, if it's a lower hill, then the better the probability that these reacting molecules will have enough energy to reach the top of the hill. So this is the reason why high substrate concentrations, high temperature, but low EA will allow reactions to happen faster. So what is the strategy that enzymes use? How do enzymes make reactions go faster? So enzymes provide a different reaction path. So you can see without the enzyme, the reaction goes with this transition state here and all the way down to the products. But with the enzyme, the reaction path is different. The enzyme reacts with the substrate, forms an ES complex, and then there is a transition state form, and then there's an intermediate form, another transition state, TS2 form, in case of chymotrypsin, and then another intermediate form called the acyl intermediate or AI, and then another transition state, TS3, is crossed before we form another intermediate, Ti2. And then before we form the products, there's another transition state that has to be overcome. The barrier has to be overcome, and then we finally get the products formed. So without the enzyme, the path is very different than with the enzyme. Now, unlike transition states, intermediates can be observed and sometimes even can be isolated. Okay, so intermediates can be observed or isolated. So these are all the intermediates. Transition states are simply predicted, but they cannot be observed and they cannot be isolated. So enzymes basically decrease the activation energy. So in the presence of enzyme, you can see the activation energy is only this much. Without the enzyme, the activation energy is very high. It's very important to note that the delta G reaction is unaffected by the enzyme. Whether you have the enzyme or you do not have the enzyme, the delta G reaction is always the same. One way to show how effective enzymes are is to calculate what we call the rate enhancement. That is, what's the velocity of the reaction in the presence of the enzyme compared to the velocity of a reaction in the absence of the enzyme. So the rate enhancement is basically the velocity of the reaction that is catalyzed by an enzyme divided by the velocity of the reaction that is uncatalyzed by the enzyme without the enzyme. And given at a given substrate concentration, we can cancel the S, we can cancel the A, which is also the same for the reaction, and we get basically, we can simplify this equation and we get a rate enhancement which is equal to e to the power of delta EA divided by RT, where this delta EA is the difference in the activation energy of the uncatalyzed reaction compared to the activation energy of the catalyzed reaction. So as you know, the activation energy of the uncatalyzed reaction is much higher. The energy of activation of catalyzed energy is much lower. So if we subtract these two, we get delta EA. In case of chymotrypsin, we can calculate the rate enhancement at 37 Celsius, 310 Kelvins. The delta EA, this difference in energy between uncatalyzed and catalyzed, is about 58 kilojoules per mole. So 58 kilojoules, that will be about 58 times 1,000 because this is kilojoules. R is given in joules, so that's why we have to calculate EA in joules and multiply it by 1,000. And if we do that, we get a rate enhancement of E equals 23. That comes out to be about 1 times 10 to the power of 10. So chymotrypsin, by reducing the activation energy by 58 kilojoules per mole, that's not much. That's basically less than the energy of a covalent bond. What chymotrypsin has done, it has increased the reaction rate over 1,000,000 billion fold. Each chymotrypsin molecule can break about 100 peptide bonds in 1 second. We call this number the turnover number, or kcat, which we'll discuss in future videos. And just to remind you, without chymotrypsin, 1 peptide bond will take years to break. So that's the miracle that we see in our body when we talk about enzymes. So that's how basically enzymes work. By reducing the activation energy, they can make reactions go much, much faster. So here are more examples of this, of the use of this rate enhancement equation. It gives us some very interesting information. So for example, in example 1, how much must the activation energy be reduced by the enzyme so that the reaction is 10 times faster at, let's say, room temperature, 25 degrees Celsius. So you can put these numbers in. 25 Celsius is 298. And then the rate enhancement is 10 times, so this is 10. And then you plug in the numbers and you see the delta EA is only about 5.7 kilojoules per mole. So the enzyme, in order to make the reaction go 10 times faster at 25 Celsius, it needs to reduce the activation energy only by 5.7 kilojoules per mole. Now, 5.7 kilojoules per mole that's less than the free energy of a weak interaction such as a hydrogen bond. Here in example 2, how much must the activation energy be reduced by the enzyme to increase the reaction 50 times, 54, at, let's say, body temperature 37 Celsius. So 37 Celsius, if you convert it to Kelvin plus 273, that comes out to be 310. Plug in your 310. 54 means rate enhancement is 50. Now you solve for this delta EA, and delta EA comes out to be 10 kilojoules per mole. That's roughly less than 1 or 2 hydrogen bonds. So we can see how fast reactions can happen in the presence of enzymes and how slow reactions would happen without the presence of enzymes. So without enzymes, we would not be able to survive because our chemical reactions would be very, very, very slow. Yes, Cooley, this is a very good example of the power of enzymes, right? So without enzymes working, you can see scientists were able to identify what this person ate almost 5,000 years ago. Isn't that remarkable? Okay, so now you should have a good idea why enzymes make reactions go much faster. So how do they do this? How does chymotrypsin make the peptide bond hydrolysis reaction in the body go so much more faster so that we can survive? That's a good question, Curly, and that will be answered in the next video. Okay, so in our next video, we'll talk about the mechanism by which chymotrypsin make reactions go so much more faster. All right, until next time, have a great day, and please do not forget to subscribe. It is free.